Okay, so how to post-process data from PFM. Probably better ways to do this than this one, but I'm just more confident with this one. So let's say you have your simulation on GID. You can export post information, which is just results, as ASCII files, which is, well, there are multiple options. ASCII files just outputs everything as ASCII. For example, you can define it just mesh NRS and you give it a name. I've already done that for another simulation for just one step. So you can see the results for this specific file. It's what it's the separates the results in mesh files here and results file. It's the same for other stuff, but since exporting the entire simulation can be quite significant, just showing here with one file. So you have the result and the mesh data, which is just a collection of node points and, well, nodes, and then for each element, it just the list of the nodes that constitute each element for each step in which the mesh is outputted. And then in the results file, it's the same, but with stress tensor, and each variable, depending if it's a scalar or a matrix, it just output, and depending if it's assigned to nodes or elements, it's just outputted. So what I've done is this matlab file called postprocess all, which what it does is just you define a file name. It checks if there is a matlab file with the same file names. If it doesn't, it opens the txt files, cycles for each line, and exports the data at the triangle mesh, solves it. So this is for now just works for today, and then does the same for each result. And it creates the file into here, for example. Well, if MATLAB is kind of frozen, no. Okay, creators, numj. It creates these two files, mesh data and results, and each result file has two steps, in which one step, well, this one has only one step because it was one individual frame. Each step has the contact, or as each individual variable for each node and for each, you can see here, 22,000 is the nodes and 24 or 44,000 is the elements. And they just export every variable you decided to export in GID. So when you set up the problem, which is not set up here, simple here, okay, when you set up the problem, you can decide which variables to export here in results, stages, results on element, so stress, strain, stress invariance, porosity. So in this case, it's extracting these variables and the one on nodes as well that you selected here. In this case, water pressure and contact force. So this just creates this specific data structure, and then using this data structure you can pretty much do whatever you want. For example, here it's some data I have. What I do is select for each step, so for each length of my results, for example, run up to here, I get a certain time. I'll wait for it to load. You have my results, which is 450 steps. Stop here. Okay, so you can see that different times have different number of nodes and elements, but for each node you have the contact force, the displacement, a traffic depth, and it's the same for the elements, which I've mentioned in nodes. So you have time, and then with this data you can do what post-processing you want. For example, here I'm doing calculating the dip load, which means I get the contact force at the specific time step index, which corresponds to time equal to 9 milliseconds. I strike the contact force. I consider only the phases in which, or only the nodes in which the contact force is positive, because if there is no contact force, there's no point considering them. And then I just consider tip load equal to the sum of the forces, for which the nodes, the second position of the node, which is the y, is lower than the minimum y, which is also defined as displacement plus tip radius. If it's lower than this, it belongs to the tip. So I just sum the forces that belong to the tip. Friction outside and friction outside is the same, but instead of considering the one with are below the minimum y, it's just the one that are within or above the minimum y and within the internal radius of the pile, and the same outside. And you can also, if you want to plot something, there are multiple functions you can use. Quiver is just for 2D variables, so if I let me just run this like this. So just x, y, fx, or value on x, value on y, and then you can also specify the scale, which is, let's say, 1, or the scaling. So just remember that in this case, okay, at the very beginning, for example, you have just 3 nodes in contact, and they have a certain force. Another function that's useful, for example, is, or what I'm doing here is doing the same, but calculating the eve. And what I do is, for each element, I have the 3 nodes that correspond to the element 1, 2, 3. So if you remember the structure of the mesh from the other file, well, the computer moved, you have, what do you call it, element number, x, y, or node number for each element. So x, y, it's not even x or z, it's just node number 1, 2, 3, and this is the same. So point 1 is nodes, where nodes is, or you get the element, for example, elements 1 is 863, so you get node number 863, and it gives you the position. So you have the three positions, x and y. You have the porosity, which in this case is just my results dot porosity for the individual step, or PT, which is the bond strength. You can calculate the area with just the cross product, the volume, which is cross product multiplied by the radius, or 2 times the radius multiplied by p, and you get the mass. And in this case, depending on the position of the element, you can sum as puttified, total puttified, or mass inside or outside the pile. Another property which is very useful is, or another function which is very useful is this scattered interpolant. So for example, if I just, well, run up until this point, what scatter interpolant does is, what I'm doing here is temp, that's just a variable, temp x, y, and pt, which for each element just stores the x and y position. I'll continue. Just store the x and y position, which I came from there. So it's x, y position, or the average of the element nodes, or the area, and the pt. And what it does here is scatter interpolant is just what you can use to find value at specific points. Continue. So it just creates, well, by default it's linear, but you can use natural neighbors or other interpolation functions. Scatter interpolant x, y, and value, or you can do in 3 dimensions as well. And then if you want the value, you just provide the x and y of the query position, and it gives you the value interpolated from all your data. So for example, if say this is your model, and you want to know a value of water pressure here, you can just load the all the nodes. You get x and y for all the nodes. You get pore pressure for all the nodes, and then you do scattered interpolant, and you feed to this scattered interpolant object the position you want to query. Here, what I'm doing is the same, but instead of just feeding it one position, I'm feeding it a matrix of positions in order to have a grid of positions, in order to have a grid of the PT, which you can then use to calculate the size of the stratified zone. But in general, I will just decide, for example, what I'm doing for the NumGen is define a few points whose position change reflect during simulation as the pile inserts the geometry, and then you just say for each step scattered interpolant of the variables in position this 1, 2, 3, 4, and it just give you the 4 different results, which is the easiest thing to do. Instead of trying to find the closest node to the position, the scattered interpolant function does this for you already. Create this object, and then you just evaluate or just feed the position to the object, and that's about it. Oh, another thing is, I don't know why, but the mesh data is typically not available for each time step. So what I'm doing is just sampling, so that if it doesn't find the data, it just says, if it cannot find the mesh, it says doesn't exist the mesh, it can't find it. Otherwise, it just does this calculation, which is just calculating Eve in and out. And well, this just creating the mesh grid, which is XX and YY, which is your mesh. And what I'm doing here is just finding the thickness of the patified zone just by doing, if I have the matrix of the patty distribution, I just do the grid. So this is just friction and Eve, whatever, which I calculated earlier. And this is just and does the gradient in the vertical direction of the path of the PT map, and then it finds where the gradient for the first derivative is minimum maximum, so the change in the change in patty concentration is minimum maximum, and uses this to define the minimum and maximum or the position of the patty zone, which is in this case T1 and T2. I don't know why it's taking so long, just because I'm running so many things. T1 and T2 just means that the internal one is 12 centimeters and the external one is 9 centimeters. And if you want to see, for example, this BV map, I can do contours, which is colored contour of BV, which is the scatter interpoint map. You can see here. And if I instead plot, this is the vertical mean, which you can see here, of the patty. So around here would be 0 patty on average. And this is peak patty where the pile is inserted. And if I do the same but with the gradient, which is just first derivative, you can see you have a maximum and a minimum, which is where your change in patty concentration is sharpest, and you just use this to define the width of the patified zone.